Morning, folks. My name is Ahmed Sanaullah. I'm a senior data scientist at Red Hat. Sorry, change of roles. I keep confusing. I work on building an open source toolchain for FPGAs. There's a lot of wonderful people involved in the project. From the Red Hat side, we have Uli Draper and Hugh Brock. We also have people working on this from the academia, such as Professor Martin, who was my PhD advisor till last year. And then also a lot of people from industry are working with us on this. So we've heard that FPGAs are being deployed in the cloud and in the edge, but that's part of the solution. We also need to be able to leverage these FPGAs effectively to truly benefit from them. And long story short, we need to be productive on these FPGAs. So what is productivity on FPGAs? Well, I like to define it very simply. Productivity on an FPGA is being able to deploy your workloads within the finite resources that you have on a chip, to do that in small time frames, and to do that with high performance. Where does productivity come from? Well, just like other technologies such as CPUs, productivity comes from the tool chain. Today, when you write CPU codes, you're just focusing on the application, and you let the tool chain figure out what's the best way to optimize this for the target architecture. Well, an FPGA tool chain, let me just get rid of the animations there. Right. An FPGA tool chain is quite similar to that of a CPU. You can start from a high-level language, such as C code, and using something called a high-level synthesis compiler, you can generate HDL code, which is the assembly language for FPGAs. You can do that either by taking vendor IP blocks and stitching them together to form your circuit, or if you're comfortable working in assembly directly, you can write your own library of components. And then you can, of course, do RTL simulations, which allow you to verify the functionality, to get estimates on performance before you actually spend hours and hours generating actual hardware. Once you're sure that's the design you want to take forward, you take that assembly code, and using a couple of processes, you generate the machine code, which we call bitstream. The first process is synthesis, where you convert the behavioral representation of hardware into a net list of gates and wires, connect them together. And then you do place and route, which basically takes this logical representation and maps that to physical resources on the FPGA. So for example, an FPGA doesn't actually have gates. It has lookup tables. So in order to implement a gate, you implement the functionality of that gate as entries in the lookup table. To be able to do this mapping, you need to know what the FPGA actually looks like, because every FPGA has differences in what is located and where is that located. So for that, you need access to that FPGA's database. Once you have a bitstream, you can push that out to the FPGA using a programmer. On the FPGA, you have a reconfigurable hardware operating system running, which does what an operating system should be doing. It multiplexes resources, isolates multiple users, et cetera, et cetera. And then you have a software runtime that allows that device to talk to host application, that allows managing of job queues. Again, what we expect a software runtime to do for external devices. The problem is that this has typically been proprietary. And there are many, many reasons why that's a bad thing. And you can think of this as any other software being proprietary. But let's look at 4 reasons here. 1, you can't customize. You're stuck with the functionality that you're given. And the alternative to that is either writing your own, which takes a really long time, or building in wrappers, which means you're going to consume more resources than you needed to get something working. Then there's licenses, and there's a lot of licenses for doing this. Sometimes you have licenses that are separate for different boards by the same vendor. Sometimes you have licenses that are separate for high-level synthesis versus just compiling HDL code to bitstream. Then rigidity of algorithms. Synthesis, placing route, for example, are core steps in generating hardware. You go from behavior to a physical implementation. But these steps have typically been proprietary. So you really just click a button and magically you have your design. You really don't have control over the algorithms, et cetera. And then finally, security. There's a lot of published work that talks about how having proprietary bit streams, not knowing what's actually getting pumped onto the FPGA, allows you to carry out side channel attacks, fault injections, it exposes numerous attack surfaces. But we, in the past few years, have taken steps. No, we've taken strides in trying to address this problem. There's a lot of work being done to open source this tool chain. There's work being done right here in BU on, for example, the high-level synthesis compiler, where we're trying to build something that's fully open source, that does not require vendor IP to form these circuits by representing code in C. There's also work being done on Morpheus, which is the reconfigurable hardware operating system, where we're trying to have one operating system that can be deployed in the many configurations, the data center and the edge that you saw in the previous talk. Then we have work that we're doing with industry partners, such as Symbiotic EDA, who have built a synthesis and place and route tool set. It's not as good as vendors. You're within 20% performance of the vendors, but it is, steps taken in the right direction, and we're hopeful of first closing that gap and possibly even going further beyond that. And then there's efforts done by the vendors themselves, the OPA software runtime from Intel and the Rapid Write tool from Xilinx. Rapid Write is basically Xilinx giving you access to the board database. You still need the vendor tools to compile the bit stream, but at least you can do your own synthesis and you can do your own place and route for their FPGAs. So in the last couple of minutes that I have, I'm going to do an example. This is something we did for my thesis. It's basically looking at high-level synthesis. Intel has this really nice tool, the OpenCL SDK for FPGAs, where you write code in C and have that compile to hardware. We picked it up a couple of years back, and we thought, let's experiment with this. Let's see how good this really is. We got miserable performance. We followed the best practices guide to the letter. We did what we thought based on all the documentation out there that this is what we should be doing. And for an application that works well in FPGAs, if you code it in assembly language, we did not get good performance. But we knew that it wasn't the compiler, because the Intel engineers actually get good performance. We knew it was something that we were not doing right. There was a disconnect between what the compiler was expecting versus what we were giving it. And so we did the only logical thing. We hacked the toolchain. We instrumented the compiler. We made it spit out LLVM intermediate representations. We analyzed these, and we saw that, yes, the compiler is expecting code to be presented in a certain way so that it can extract the appropriate hardware primitives from it, and we're not giving it to it. And so we tried to take it this one step further and generalize the process, generalize the approach. Basically, we wrote a suite of probes that we run through a high-level synthesis compiler once. We take the intermediate representation data, we run it through a static profiler, and that tells us what the compiler wants to see for these basic FPGA designs that we want to build. For getting a SIMD out, for getting pipelining out, for doing caching in our hardware design. And then, taking the results of these profiler, we can then apply a set of systematic code transformations to our C code to actually then bridge that gap between us and what the compiler expects. And we actually got very good performance for it. We tried it for a bunch of network packet processing workloads. That worked really well. We tried it for a bunch of high performance computing workloads, and we got really good performance there. So what was so good about this? This was not a case where the algorithms were bad. This was not a case where the compiler was bad. But because it was proprietary, we just didn't know how to use it. There was not enough documentation out there for us to be able to actually leverage this important tool. But by being able to see under the hood, by being able to access all this intermediate representation, by being able to see what the compiler saw, we were able to actually improve our code structures. We were able to tell the right things, write the right code to be able to get this performance. And that's my talk. Thank you so much for listening.